In this video, we want to determine the eigenvalues and eigenvectors that are associated with this particular matrix. Before we get into it, we want to point out that the playlist for all the videos is at the website digital-university.org. Now, if you've watched the other videos in our linear algebra series, I think it was videos 15 and 16 when we explored the eigenvalue, eigenvector problems in considerable detail. In those videos, we had, for example, a 3x3 matrix. There were three different eigenvalues associated with the matrix, and for each of the eigenvectors that corresponded to that particular eigenvalue, the eigenvectors that are associated with distinct eigenvalues, they are linearly independent. We haven't proven that yet. We will probably prove that in video number 23, or 23 or 24. It's coming up anyway. And that's important. We actually used that knowledge in a previous video without proving it when we worked on diagonalization. I think that was back in videos 18 and 19. Remember how that was set up. We had a matrix, just to take a 2x2 example. Here we had a matrix, and it has associated with it two eigenvectors. They're linearly independent, and we took their components and made a matrix out of them. And sometimes this is called the M or model matrix. And matrix A times matrix M equals matrix M times a diagonal matrix. Remember, in the diagonal matrix, the diagonal elements on that matrix is just simply the eigenvalues associated with these two eigenvectors. And again, we discussed that in a lot of detail in videos 18 and 19. The point is that since these eigenvectors are linearly independent, then this matrix has an inverse. Multiply both sides of the equation by the inverse, and we derived this expression. So we can take a matrix and we can diagonalize it if that matrix has a full spectrum of eigenvectors. That is, if this is an n by n matrix, then it would have to have an n number of eigenvectors associated with it. That doesn't always happen, of course. Therefore, not all matrices are diagonalizable. And so far, all the problems that we have worked, we had eigenvalues that were distinct. What happens if they get repeated? And that's what we want to examine in this video. So here we will have, to determine the eigenvalues, 0 minus lambda is minus lambda, 1, 1, 2 minus lambda, 1, so we have that determinant set equal to 0, and now we want to find out what is lambda. So we go ahead and we expand by minors, and the expression we get is minus lambda times 2 minus lambda squared minus 1 plus 2 minus lambda minus 1 minus 1 minus 2 minus lambda. Expanding this out using minors, expanding along the first row, and that has to equal 0. So here we will have minus lambda times 4 minus 4 lambda plus lambda squared minus 1 and 2 minus 1 is 1, so we have 1 minus lambda. And here we have 1 minus 2, that's negative 1, minus negative lambda. Inside here we have minus 1 plus lambda. This is being multiplied by minus 1. So here we will have plus 1 minus lambda multiplying through equals 0. And multiplying through here by minus lambda, we have minus lambda cubed plus 4 lambda squared. 4 minus 1 is 3 times minus lambda. And then from here we have minus 2 lambda plus 2 equals 0. So simplify this and we have lambda cubed plus 4 lambda squared minus 5 lambda plus 2 equals 0. So our characteristic polynomial is a cubic one, and we can find the roots for cubic polynomials using synthetic division. We won't go through the whole process in this video, but if you're unfamiliar with that, if you go to the website and then go to the calculus playlist, open that up and scroll down, you see we have a whole section there where we have problems that we solve using synthetic division. And here, for our particular problem, this factors out to be minus, then we have lambda minus 1 squared times lambda minus 2 equals 0. So multiply both sides by minus 1. This is irrelevant. So we have lambda minus 1 times lambda minus 1 times lambda minus 2 equals 0. So we have 3 lambdas with repeated in value. We have lambda equals 1, lambda equals 1, and lambda equals 2. Now we know the eigenvector associated with this will be linearly independent of the eigenvector that's associated with this, because these lambdas have different eigenvalues. As we said before, eigenvectors that are associated with distinct eigenvalues are linearly independent. We will actually prove that in a future video. But what about here? Here we have an eigenvalue of the same repeated twice. What's going to happen in this situation? So in order to see, let's go ahead then and determine the eigenvectors that are associated with these values. So we have lambda equals 1, lambda equals 1, lambda equals 2. What are going to be the eigenvectors? That's what we need to do next. If this video gets too long, we might have to split this up into 2 parts. Okay, we have lambda is equal to 1. So I'm going to substitute that into here. And then that should be pretty straightforward to handle, actually. We will have minus 1, minus 1. 2 minus 1 is 1. And that matrix times these are now the components of the eigenvector associated with lambda equals 1, and this has to equal 0. Remember how that was set up in the previous videos? Here we have an eigenvalue, eigenvector generic equation, but it's going to end up like this, so that the eigenvectors of A are in the null space of this matrix. And again, that's how we did it in all the previous videos, and that's what we have right here. A minus lambda I, that's this matrix here, and then here's x1, x2, x3, the components of that eigenvector, and this particular eigenvector associated with lambda equals 1, that particular eigenvector is in the null space of this matrix. And of course this is column x1, column x2, column x3. And if we just add these rows, we see what's going to happen. These are just going to be zeros. So we'll do that and then write it in augmented matrix form. So we'll have minus 1, just simply adding these rows here was a real simple thing to do. And then writing this in, we should have it like this actually. That is a 0 vector it's equal to. And then writing this in augmented matrix form, we have okay, and we see that, and again, here is the column for x1, x2, and x3. So look what happens here now. Here we look at this and we see that x1 is a lead variable, and there are no other lead variables here. So x2 and x3 are free variables. So x1 is a lead variable, x2 and x3 are free variables. And again, we explained lead variables and free variables back in videos 4, 5, and 6. We took a lot of time because they're very important. Because what we're going to do is we always express the lead variable in terms of the free variables, which we can do in just a moment, but also remember that the dimension of the null space equals the number of free variables. And we see there's two free variables here, x2 and x3. So that means the dimension of the null space here is 2. So there's two linearly independent vectors in this null space. Well, any vectors that are in the null space here are the eigenvectors for matrix A. So what we know so far is that for lambda equal to 1, it gives this matrix, and we'll have two eigenvectors associated with that. How do we know that? Because the eigenvectors lie in the null space of this matrix, and with two free variables, we know then that there has to be two linearly independent vectors in that null space. And we discussed null space and the dimension of the null space. I think it was in video number 4. So let's see how this turns out. Here we have minus x1 minus x2 minus x3 equals 0. And we express the lead variables in terms of the free variables. So here we're going to have then x1 equals minus x2 minus x3. So the lead variable is expressed in terms of the free variables. So now vector x1 has 3 components. Well, the first component, x1, that's this. So we have minus x2 minus x3, and then x2 and x3 themselves are free variables. So we just place them in, and this then this right here is the eigenvector. Its three components are this. Now we can make this into a better expression by factoring out the x2 and the x3, which we're going to do as soon as we make some space for that. Let's do it here. So this, if we factor out the x2 and x3, we're going to have x2 times minus 1, 1, and 0, plus x3 times minus 1, 0, 1. So this is equivalent to this expression. x2 and x3 are free variables. They can be anything. And these right here then are the two linearly independent vectors that span the null space of this matrix. But more important to us, these then are the two eigenvectors associated with lambda equals 1. So what we have here is this. When lambda equals 1 and we form this matrix right here, for this particular problem, this matrix, the dimension of the null space is 2, because for this particular problem it has two free variables. Therefore, that guarantees us two eigenvectors. So each one of these has an eigenvector associated with it. What's more, the eigenvectors are linearly independent. They're the basis of this null space. So here they are, minus 1, plus 1, 0. And minus 1, 0, 1. So here, the repeated eigenvalues each has an eigenvector associated with it. This won't always happen. As you see in other videos, we'll have a repeated eigenvalue. Maybe it's repeated 3 times, but there's only 2 eigenvectors associated with it. When you see repeated eigenvalues, the number of times it's repeated is called the algebraic multiplicity. So of course this has an algebraic multiplicity of 2. The number of eigenvectors that are associated with this identical eigenvalue, for this problem it's 2, that's called the geometric multiplicity. And then if we went ahead and continued on with the rest of this problem, where we considered lambda equals 2, you won't solve all of it all the way through, but we'll set it up. It's pretty simple, actually. But now here, if we have lambda being equal to 2, put that into here, then we will have minus 2, 1, 1, minus 1, 0, 1, minus 1, 1, 0. Putting lambda equal to 2 here. Then this times and this is now our eigenvector associated with lambda equal 2. And if we reduce this now, use our Gaussian elimination method and get that reduced, what we end up with is this is rho equivalent to remember this, we'll write it like this. It's row equivalent to this. We multiply this by minus 1/2 and add and do some other very simple row manipulations. We have minus 2, 0, minus 2, 0, minus 1, 1, 0, 0, 0. And write the whole thing as an augmented matrix. It will look like this. Now look at what we have. Here's the x1 column. Here's the x2 column. Here's the x3 column. We see that x1 is a lead variable, x2 is a lead variable, leaving x3 as the free variable. So x1 and x2 are lead variables. x3 is the free variable. Only one free variable, so there's only going to be one linearly independent vector in this null space, meaning that for lambda equal 2, there's only going to be one eigenvector then. And again, what we always want to do is express the lead variables, x1 and x2, in terms of the free variable. And in here we see here minus x2 plus x3 equals 0, so we have x2 equals x3, and then from our top equation we're going to have x1 equals minus x3. So x1 expressed in terms of the free variable is minus x3, x2 equals x3, and then we just have x3, a lead variable. So this is the eigenvector when lambda equals 2, and we can factor out the x3, and we have minus 1, 1, 1. x3 is a free variable. It can take on any value, so we can have it when it just equals 1. The corresponding eigenvector then when lambda equals 2 is minus 1 plus 1 plus 1. Like this. So for this particular matrix, even though we had a repeated eigenvalue, we still had 3 linearly independent eigenvectors. So this particular matrix should then be diagonalizable. What we'll do in the next video, though, is consider a situation where we have a repeated eigenvalue, but we don't have multiple eigenvectors associated with it. And we'll have sort of a breakdown then of what happens in that kind of a situation. Okay, that's it for this video. Come back, join us in the next video. We're going to take a look again at the repeated eigenvalue problem, one that gives us a different outcome.